So please welcome Henrik.
Okay, yeah, so I start by thanking the organizers for the invitation to come here. It's my first time in Taiwan and enjoying it. Yeah, so I will talk about this topic, which is how to couple Yang-Mills-Einstein theory. And it's going to be at the level of scattering amplitudes. Of course, it's well known how to do it in general, but this is going to be specifically for scattering amplitudes and how to simplify calculation when you're talking about Einstein-Yang-Mills theory. And this, for those of you who haven't heard the things that I'm going to talk about today, it's probably going to be in for a bit of a surprise. One surprise is how alien the thing is that I'm going to do, and another thing is how simple they are. So in particular, so this talk is based on this most recent paper by Marco Chiodroli, Murat Günaydin, and me, and Ryder Royman. And of course, it's based on earlier papers, but this is the most recent one. So the slogan of today's talk is that I want to construct scattering amplitudes in general relativity coupled to Yang-Mills theory. And I want to do it in a very funny way, where I express it as a double copy of Yang-Mills times Yang-Mills plus a scalar theory, and this is going to particularly be phi cubed. And this looks probably pretty alien to you. So this is the slogan of the talk, but this is also a very precise statement. If I make it if I specify the details, of course, and this is part of a more general framework where we sort of look at gravity theories and decompose them as products of two different gauge theories, and this is a particular one way of doing this. And in particular, what I will talk about today is scattering amplitudes. Because that's the only framework we know where we can make this statement precise. And so we'll look maybe a bit specific to dealing with on-shell quantities, or a bit narrow. But on the other hand, it's quite general because it will be general to, not specific to a theory, so it will be generic super Yang-Mills, or a supergravity. And it won't be specific to the space-time dimension either. So any space-time dimension D. Okay. So
should I think of this as being analogous to the heterotic string?
It's quite analogous, yeah. But it's the details are on one hand it's quite different, the construction in details, but certainly the construction will be what you get when you take the field theory limits of the heterotic string.
Could you derive a similar relation by following the KLT argument?
Yeah, this will be part based on KLT, but it also would go beyond KLT, because this will be not just at tree level but also at loop level. Okay, so in order to explain it, let me go to some background. So maybe I should write up what downtime is going to be. So first of all, there's going to be some motivation. And then I'm going to talk about what's known as color kinematics duality. And then double copy. And then by tomorrow, well, I will get to some examples. Which will be on amplitudes, specific amplitudes. And then by tomorrow I will get to this theory, which is it's a Yang-Mills theory. And I might get to some other stuff if I have time, but that's based roughly the outline. So let me start by saying something about color kinematics duality before I say a bit more about motivation. So this is, first of all, this is from a paper going back to 2008, and it's by Byrne, Carrasco, and me. So what we noticed in that paper is that in a specific way you can say that Yang-Mills theory has two copies of Lie algebras. So there's a what we can call a kinematical, and then there is the usual one, which is just color. And that these two are, they behave in the same way. So that's why the origin of the word duality is that these are on equal footing to each other. And specifically, what you can do is that you can construct a theory which just have two copies of kinematical Lie algebras, and this is how you get the gravity. So that's a double copy. Of Yang-Mills or of this kinematical. So this is a paper from, I said, 2008. And there's another paper, 2010, which builds upon that. Okay, so this is basically, well, I don't know if there's a definition of the things, but that's an introductory statement. So now let me say a bit more motivation, why I'm interested in looking at scattering amplitudes in this series. And why I'm interested in doing it in a different way than the standard way. So the standard way to do perturbation theory in gravity, it's to write down the Lagrangian of gravity, which I write like this. And I'm not sure if I had a minus sign, right? But this, so it's just a gravitational coupling constant, which I call kappa here, which is square root of appropriate dimensionful quantity. And then what I do is that I expand the metric as there is a Minkowski space, or Minkowski piece, and then plus some perturbation. And then at this level it looks pretty simple, but of course in here there's also the inverse metric, and then there's the square root of the determinant of the metric. So once I expand this whole thing, I get a very complicated perturbative expansion for the different vertices. So just to give you a flavor, so if you just look at the propagator, this has 3 terms. I'm not going to write them out. And then if you look at the cubic vertex, it has on the order of 100 terms. and then so on. As you get to the 4-point vertex, there's roughly 10 to the 4 terms, and so on. And this is why it gets very complicated, because if you want to do some specific calculation, let's say you want to do a simple one loop 4-point calculation, you can calculate how many, or count how many terms there are in this calculation. So in particular, there's 3 propagators, there's 4 propagators, 3 to 4 terms from that, and there's 4 vertices, so that's 100 to the 4th power. And I haven't worked out what that is, but I guess this is roughly, I guess it's 10 to the, 8. You can correct me if I did it wrong. So it's a large number, and this was just the simplest 4-point one-loop quantity that you can do. Of course, as you go higher and higher loops, it gets worse and worse, and at some point, it's literally impossible to store all the information from this terms in the diagrams. So this is a standard way of calculating scatter amplitudes is very complicated, and from this you might just say that, well, it's complicated because gravity is a complicated theory, and that's it. But in fact,
do you fix the gauge?
Yeah. So this is the Donner gauge. But, well, I didn't write out the details, but a standard gauge choice is the Donner gauge.
In the loop, you don't have a ghost?
It just goes, yes, there goes at loop level, just like in Yang-Mills theory. But okay, so what's the reason to expect that there's any kind of simplifications in gravity? Maybe this is it, maybe there's nothing further you can do. Well, so let's look at some quantities which are more well defined than ephemerals, which are more physical than ephemerals. So in particular, the most simple thing we can look at is just a plane wave. So let's start with that. So my plane wave here is just a free particle. I can assume there's no interactions. So then, of course, the metric is very simple. It's just some polarization tensor, and I'm going to factorize it into this form. And then there is a standard plane wave factor. I'm going to forget about that, minus signs and so on. So this is a very nice and clean form, but of course it's a free theory, so that's expected. But the nice thing here is that what I've done is that I factorized the polarization tensor into 2 pieces. And each of them is a polarization vector of the Yang-Mills theory. So we can correspondingly compare it to what if you had a free, if you have a non-interacting gauge theory, and just write down the plane wave, so for example, abelian QED. So then it looks pretty much the same, except that you have just one factor. And then you can compare that, well, what if you just have a scalar field, a non-interacting scalar, you would have this plane wave. And it's a beautiful structure here, that it's the same factor that appears here, and then there's additional polarization vectors showing up that you multiply on top of that. Of course, that's very reminiscent how it works in string theory, so no big surprise for the vertex operators. But anyhow, so this is the free theory, so of course it should be simple. But could we expect to see similar simple structure if you look at interacting series? So indeed, if you look at the 3-point amplitude, 3-point amplitude, or the on-shell 3-point vertex, you can rewrite it on this form. So first there's a gravitational coupling constant. So I said before that there was a 100 terms, but I'm just going to write down actually the ones that contribute, because this is going to be on shell. So all the 3 legs are on shell, and therefore there's a lot of simplifications. And I'm going to call them like 1, 2, 3. And each leg is going to have a mu index and a nu index. So let me write down the things which have a mu index first. And it's the same thing here. So mu1, and nu1, nu2, k1 minus k2, and nu3 plus psi. So these are all the terms that contribute when you place all the momenta on shell. So all the momenta here are called k. So all the ki squared are equal to 0. And you might recognize these 2 factors. Well, I didn't write them out completely. I just wrote the first term and then I said cyclic. This is the same factors that appears in your standard Yang-Mills theory. So if we would do the same calculation, or the same 3-point amplitude in Yang-Mills theory, this part here would be the same, but here we would put a F, A, B, C instead. So that would be, this would be Yang-Mills. So here again you see this interesting structure that the same object that appears in gravity also appears in Yang-Mills, or vice versa. But that some of the kinematical part is replaced in this case by color factor because it's a non-abelian theory. Now you could have shown this in another way by just looking at the possible structures that can show up for 3-point amplitude. And then you can convince yourself, well, it had to work this way because the 3-point amplitude is actually restricted by Poincare area invariance and so on. So all actually symmetries completely fix this object, and maybe therefore it's not so impressive. But if you look at further quantities, higher point quantities, which are not fixed by symmetries, it still works the same way. So in particular, let's look at a 4-point amplitude. Let me denote it M3, 4-point, 1, 2, 3, 4. So very schematically, I just draw the leg labels here, 1, 2, 3, 4, as arguments. So this amplitude is known to factorize on this format. So the A's are Yang-Mills amplitude, and the M is a gravity amplitude. So again, the gravity amplitude factorizes into 2 Yang-Mills amplitude. And in this case, this is a color ordered amplitude. Well, in string theory, this is just what's known as a disk amplitude. It's essentially is the piece which is proportional to the trace TA1, TA2, TA3, TA4, and so on this one. So it's interesting again that it does factorize into 2 pieces. There's some additional kinematical factor here. It's there to take care of the dimension. If it wouldn't be there, the dimension wouldn't be right. It's also there to take care of the extra poles, because this amplitude has a pole in the S channel and the T channel, and this amplitude has a pole in the S channel. So there's an overcount of the S channel poles. Oh, sorry, I had the wrong labeling. This should actually be the same labeling here. Yes. So in fact, both amplitudes have poles in the S and T channel. So there's actually too many poles here. So this factor S and T cancels out this over counterpoles. But none of the two amplitudes has a pole in the U channel, so that's why this factor is here. Okay, so these kind of formulas has been known for a long time, and they're known as Quine-Llewellyn and tie relations. Let me explain what that is. So KLT, which is stands for Kawhi. Let's see. Oops. Where is it? Oh, there. Kawhi. So in '86, they wrote down a formula. Or a first example of a formula which relates different closed string series, closed string theory amplitude to open. So they wrote it as a product of open, so open so in exactly the same way as I wrote this here, they wrote it, and in particular, what you can see is that for the free string, this is sort of obvious that the closed string can be decomposed into a left-moving open string and a right-moving open string. But furthermore, they did it for the interacting, for the S matrix. And in particular, you can get relations such as the one that I wrote there, but a more standard way of writing it is just to do this. So S12, which is the same as S, and then 1, 2, 3, 4, 2, 1, 3, 4. So essentially, the way the structure is that you're summing over various different color orders of one gauge theory amplitude, and then you have different color orders of the other factor. And then you multiply by a local polynomial of the proper dimension. And this can be generalized to higher multiplicity. So this is the first instance of the 4-point amplitude, which is very simple. At the 5-point case, 5-point amplitude, there's actually a sum of two terms. And then as you go to higher amplitudes, it gets a bit more messy. But there is a formula, there's a more general formula that you can write down, which is, well, schematically, it has something like this. So there's some, so I don't need this. But so let's say you have n legs. You can write it down as, or we have different permutations. And then we need some factor that takes into account these dimensionfold parameters. So we're just going to call it S. And this is going to depend in particular on the ordering here, so the permutation rho, and it's going to depend on the permutation sigma. And then all you do is you sum over rho and sigma. So roughly that's how the formulas looks like in KLT. And this function here is known, Johansson multiplicity, but it's a rather complicated polynomial. But in this way, all the tree levels, so this is only for tree, all the three level amplitudes of just Einstein gravity or supersymmetric cousins of Einstein gravity, they can all be written on this format. Okay, so what's the what is this color kinematics duality then? How is this related to KLT? Well, let me first describe it in the context of gauge theory itself. So we noticed that there's a certain way to rewrite the amplitude. So this is just Yang-Mills theory. So now I'm going to color dress my amplitude. So I'm not going to consider this color strip. So I use a curly A for that. And then I have some loop order. And let me also call it, instead of calling it n, the multiplicity, I'm going to call it n. So we're going to write this as a sum over cubic diagrams. Each diagram is going to be a loop amplitude, so there's going to be integration. And in particular, it's going to be in any dimension, any loop order. So we have the following measure. And then we have a specific way of writing the diagrams. So we write it as a numerator, a color factor, and a denominator factor. And we're only going to sum over the cubic diagrams. So even though Yang-Mills theory has 4-point vertices, contact diagrams, we're going to massage the amplitude into this form. And you can always do that. You can always, if there's a missing, there's a contact vertex which has a missing propagator, you just promote it to have a propagator, and then you multiply by the inverse propagator in front, and then you absorb it into the numerator. So this can always be done. So let me say a little bit more about what these functions are. So there's also a symmetry factor here, which I forgot. So in particular, color factor, so let's assume we're in a joint. Then the color factor is simply a product of FABCs for all the vertices which are inside the diagram. So the diagram is going to call I. And typically, when we do high loop calculations, we just refer to each diagram as a number. Diagram 1, diagram 2, diagram 3, etc. So that's why I call it I. But it's a diagram. So it's just, product just runs over all the vertices. This is just a usual way of dressing a Feynman diagram with color factors, with FABCs. The denominator is just a product of all the propagators in the diagram. So J are all the edges, I guess. Diagram J of diagram I, sorry. It's just the usual propagators that you find in scalar phi cube theory. And then what are the numerators? So the numerators are the most difficult one to describe. So I'm not going to define what they are. In general, you have to solve for these numerators, but typically the way the numerators look like is that they have some polarization vector for some leg, like say leg 1, and that dotted into some momentum, say P2. And then you have more polarization vector, which can be dotted into some other polarization vector, and then you have momenta which